Okay, so we've talked about series sequences and series, and then we spent the last couple of days talking about what does it mean for a sequence to converge or diverge. We saw lots of examples of that. You had that in your homework. So now, what about a series? What does it mean for a series to converge? So an infinite series converges. What's a series again? Try that again. What's a series? It's just a big, long sum, right? All it is just adding up the terms of a sequence. That's what a series is. So what would it mean for a series to converge? It would mean if that sum sums up to a single finite value. That's what it would mean for a series to converge. All right, so practice warm up here. So I want you to represent the sequence, the series, and the sequence of partial sums only with symbols that a third grader would understand. The sequence, the series, and the sequence of partial sums, but only using representations that a second or third grader would understand. Okay, so we already did that, but I'm gonna do it again fast here. All right, so the sequence is, remind me, 3 halves, then 4 fifths, 12 fifths, 27 tenths. Okay, that's enough. There's the sequence, the series. Add them together. Okay, then the sequence of partial sums. What's the first in that list? 3 halves. The next in that list, 3 halves plus 12 fifths. The next in that list is the sum of the first 3. The fourth partial sum would be the sum of the first 4, and you make a list of partial sums. That's the sequence of partial sums. Okay, does this sequence, does it converge or not? Does the sequence converge or not? You are experts at this now, right? Some are saying yes. Do you agree?
Yes.
What does it converge to? 3. We got a rational function. Degrees are equal, so when I gets really big, we're just going to basically get 3 over 1. So I'm going to kind of rewrite this as, so when we get to the millionth term, that term is essentially what? 3. And when we get to the next term, what's the next term? Essentially 3, actually a little bit closer to 3. So what I mean by this is, technically it's not exactly 3, but it's so close to 3 that we just call it even, right? I mean, when you plug in a million or a billion or a trillion into this is an infinite sequence, you're going to get a number so close to 3 that it's basically the same as 3. So that's what I mean by putting parentheses around there. So when I gets really large, this is kind of what happens with the sequence. Does it make sense? So technically those aren't exactly 3, but they're so close to 3 and they're getting even closer with every term. So let's talk about, so the infinite series then, sum of CI, then looks like this. And when does it stop? Never. It's an infinite series, right? So do you see that the infinite series, we could write it like that. Then the values are getting closer and closer to 3, and then eventually they're just essentially the same as 3 for all practical purposes. So what about the infinite series? Does it converge, right? It converges if the sum is a finite value. Does it converge or not? Some are saying no. Does it converge? What happens? We end up doing what? Yeah, you just keep adding 3 over and over again, and you never stop adding 3. Is that going to converge to a particular real number? No, right? So this series diverges. Why? Because the sum never stops growing. It does not sum up to a particular value. It just never stops growing. Does that idea make sense? So then, why are we talking about series converging, right? If you add an infinite number of numbers together, isn't that always just going to get bigger and bigger and bigger? How could it not just keep getting bigger and bigger and bigger?
The numbers get close to 0.
Okay, Tom, what are you going to say?
If our series converges to 0, then eventually at some point,
If wait, say that again. If what?
If our sequence converges to 0, it'll be like kind of like a cone inward, and then eventually the area accumulated in those later values will equal 0.
Okay. I'm not talking about area. Be careful. So there's nothing to do with area. But so yeah, imagine that if these values were what? If these were essentially 0 plus essentially 0 plus essentially 0, then this sum could add up to something finite. So let's see that. All right, so the sequence converges to 3. The series does not converge because we end up just adding 3 over and over again, right? Okay, this one. Does this sequence converge?
Yes.
He says yes, agree? What does it converge to? 0. So this sequence is, di is, what's the first? 4/3? 4/6? 4/11? 4/18? Am I doing it right?
Yeah.
And so then when we get to the millionth or billionth or trillionth term, essentially the terms will be 0 because the sequence converges to 0. Technically, exactly, not 0, but practically 0 and getting closer to 0 all the time. Now, what about this series? Yes, okay, this will converge. This series will converge. Because in the end, we just keep adding essentially nothing, right? So it will continue to increase. The sum, so let's talk about the sequence of partial sums. So let's write out the sequence of partial sums. That'll help. First in the sequence of partial sums is 4/3. Next one? 4/3 plus 4/6. Then? Then? Do one more. Right. So I asked the question a couple of classes ago. What does this, and now I'll ask again, how does the sequence of partial sums, this one I'm writing out now, how does it relate to the infinite series? How does the sequence, this list, how does this list relate to the sum of all of the values, right? So the series is 4/3 plus 4/6 plus 4/11, and on and on and on. Dot, 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 plus practically 0, practically 0, practically 0, and on and on and on, right? How does this sum relate to this sequence? What's the relationship between this? Do you see that they're highly related? And so exactly how are they related? Can anyone articulate it? Yeah.
It's like the series that is the accumulation of
Okay. So the sequence is like, it's like building the series step by step, right? Every time you go to the next term of the sequence, what? It's kind of a little bit more like the series. Do you see that? So if you took a value way out in the sequence, way out at the end, not at the end, there is no end, but way out, say the millionth term of the sequence, it would be the sum of the first million terms of the series, and it'd be practically the same as the series. Do you see that? So how do we say that mathematically? How do we say that mathematically? That this is becoming more and more and more like the value of the series. Mathematically, what is that? What am I talking about? Yeah, the limit. It's what this sequence converges to. What does it converge to? You keep adding one more term of the series each time. You're getting closer and closer to the whole series. So the farther out you go in that sequence, the closer you are to the series. You keep making it one term closer and closer. Does that make sense? So the limit as I goes to infinity of the sequence of partial sums equals what? The series, the sum as I goes from 1 to infinity of, how do I express the series? Capital S? I should be using D, but little s, right? So if I sum up all the terms of the sequence, that's the same as what the sequence of partial sums converges to. Every partial sum gets closer and closer to the value of the series. So these become approximations of the series, right? And each one gets better and better because you're adding one more term each time. So the limit of the sequence of partial sums is the same as the sum of the infinite series. It's a super important concept. It has to make sense, not just something you memorize. Any questions on that? So that's what I said. The sum of the infinite series is the limit of the sequence of partial sums. So that's what I just wrote in mathematical form. Okay, so there's the first theorem here. The divergence theorem lets us conclude quickly that an infinite series diverges if the sequence has a qualifying feature. So how would we know instantly that a series diverges? By looking at the sequence. What would you say about the sequence that you could say, oh, that series would have to diverge right off the bat? Based on what we've just been talking about. Yeah. Okay, if each term is increasing. Okay. Yeah.
If the degree of the exponent is greater is greater than the degree of the
That's for only a specific class of sequences, right? So I'm just talking about all sequences now. So that would be maybe rational sequences, but for all sequences, yeah.
If it does not converge to 0.
Right. So if the sequence doesn't converge to 0, then summing them all up could never sum to a finite value. Right? So what kinds of sequences are such that we can immediately conclude the associate series diverges? If that sequence does not converge to 0. Like the first one we saw. What if it converged to 3? So then we ended up adding a bunch of 3s. In the series, you just keep adding 3 plus 3 plus 3 plus 3. It's never going to converge, right? So the series of the sequence AJ diverges if that sequence does not converge to 0. So this is always going to be the first thing when checking series. So we're going to learn lots of different ways to check series for convergence or divergence. This will always be the first thing you check. If your sequence doesn't converge to 0, game over. The series cannot converge. That's the divergence theorem. So the only series that converge are the ones whose sequences converge to 0. Why? Because you're adding all the terms up, all infinitely many terms. So those terms have to get really, really small for the series to converge. If they don't, the series isn't even worth analyzing. If the sequence doesn't go to 0, we don't even have to analyze the series. We're just done. It diverges. Doesn't make sense. Okay, so let's look at one called the harmonic series. This is the harmonic series. So first of all, looking what's the sequence that builds the series? What's the sequence? What is the sequence? 1 over j, right? So this is always the sequence. And then is that any particular kind of sequence? He's saying it's a p sequence. Is it a p sequence? Or not? Blank stares. Still heads. Is it a p sequence or not? And what's the value of p?
1.
So this is 1 over j to the 1, where j goes from 1 to infinity. That's a p sequence with p equal to 1. Does the sequence converge? Does the sequence converge? And what does it converge to? 0. P sequences as long as what? So p equals 1. And what's our condition for a p sequence to converge? Positive number, right? P equals 1. That's greater than 0. Therefore, the sequence converges and converges to 0. Right? Makes sense? What do we got? We got denominator getting really big. 1 over a billion, 1 over a trillion, 1 over a gazillion, right? 1 over a Google. What's a Google? You know, Google is a number. 10 to the 100. That's a Google. Okay, so that sequence is going to get as small as you want, as close to 0 as you want, essentially practically 0. Okay? So write this out. Write out the series the way a second grader would understand. Write out the series the way a second grader would understand. And where's Lisa Wen? Where's Lisa? Lisa here? Lisa Wen? How about Savannah? Where's Savannah Miller? Yeah, did you get it? So you're making a list? The series. So write out the series as a second grader would understand. What's the series? Okay, that sounds like the sequence of partial sums. What is the series? Where is Jace? Is Jace here? Yeah, tell me. That's it. So we're just going to add up all the terms of the sequence. 1 plus 1/2 plus 1/3 plus 1/4, and on and on and on. Okay, so the sequence converges to 0, right? The sequence. So what about the series? Does it converge or diverge?
Diverge.
What do you think? Converges, right? Because it goes to 0. All right. So we've already answered these questions. It's a p-series, p-sequence. So since the sequence converges to 0, can we conclude that the series converges? Okay, let's take a look. So I'm going to write a different series here. And so this series, instead of 1/1, 1/1/2, 1/3, 1/4, I'm going to do 1, 1/2. And then instead of a third plus a fourth, I'm going to do a fourth plus a fourth. Okay? Instead of a fifth plus a sixth plus a seventh plus an eighth, I'm going to add 4 1/8ths together. And then starting again from 1/9 all the way to 1/16, instead of writing that, I'm going to write all 1/16ths. Does it make sense? Okay. So, what is 1/4 plus 1/4? What is that? That's 1/2. And how does that compare to 1/3 plus 1/4? Is 1/2 less than or greater than 1/3 plus 1/4? Less than, right? This is less than 1/2. Okay, the next 4 terms of this new series that I made up, what do those equal? 1/2. What about 1/5 plus a sixth plus a seventh plus an eighth? More or less than 1/2? More. Bigger. So really, I should have put this is greater than 1/2, right? And what about all this? Greater than 1/2. Next one. The next 8 terms, 1/16 equals 1/2. And how about then these? Greater than 1/2. Okay. Do I ever run out of terms? Can I always double the number of terms I had before and get 1/2 in this one? And then if I do the same thing up here, I'll always get a number what? Greater than 1/2. So I got 1 plus 1/2. The next 2 give me a number greater than 1/2. The next 4 give me a number greater than 1/2. The next 8 give me a number greater than 1/2. The next 16 will give me a number greater than 1/2. And I can always double the number of terms I had from before, and the sum of that group will be greater than 1/2. So what about this series? Does it converge? No, I can always get enough terms to keep adding a number more than 1/2. So the harmonic series converges or diverges? Diverges. Uh-oh. Doesn't that contradict what we said? Does it contradict what we said? It doesn't contradict what we said. What we said is, in order for the series to converge, the sequence has to go to 0. But we never said that the sequence going to 0 will assure or guarantee that the series converges. What we said is, in order for a series to converge, the sequence has to get small, has to converge to 0. Okay? But we never really said that that guarantees it. It doesn't. The sequence going to 0 doesn't guarantee that the series converges. Because here's a case where the sequence goes to 0, but that series still diverges. Got to keep this, it's super important. Got to make sure you understand that. Keep that straight. So, whoa. So what's our refined conclusion? If the sequence converges to 0, then what about the series? Maybe. It might converge. Sometimes yes, sometimes no, depending on the series. You're telling me there's a chance. So that's all it is. There's just a chance, right? It's not that it guarantees the series converges. The sequence converging to 0 means now we have a question to ask, right? Now we actually have something interesting. Now we have to analyze that series to say, does it converge or not? Because it still might diverge. But if the sequence doesn't converge to 0, what can you say about the series? That's the divergence theorem. If the sequence doesn't converge to 0, that series could not converge. It diverges. Okay, so if that's hazy, keep work on it. What we just covered in the last 10 or 15 minutes is super important for understanding series. So go back, watch the video, pause it, think about it, talk with it with classmates, TAs, myself. That's a really important concept that we just went over. Okay? We got time for geometric series. So we'll talk about P series next time. Geometric series. So what form would a geometric series have? Remember what a geometric sequence was? R to the I, okay? So that was our basic geometric sequence. So geometric series has a little more to it. It allows also for so you see this is essentially the same thing, but it allows for a coefficient, which will be the same on every term. So constant coefficient. And then we'll talk about what the effect of the j minus 1 is. But before that, I want you to write out what does this mean in a way that a second grader would understand. So when you see that, you think what, right? You see that, think what? Go. See that, think what? Everyone write that out. Where's Caitlin? Caitlin here? Trejo? Oh, right there. How'd you do? Tell me.
I wrote out AR1 minus 1.
And what's 1 minus 1?
To the R
What is 1 minus 1?
0.
Okay, yeah.
Plus AR2 minus 1.
Which is?
1.
Okay.
Plus AR3 minus 1, which is 2. And then plus AR4 minus 1, 3, dot, dot, dot.
How'd she do? Get it? Awesome. Okay, and this first one is just essentially what? A. Not essentially, it is. Okay, so what is the j minus 1? Rather than being just to the j, what does the j minus 1 do? It makes the first term just be a, right? So the first term is just like a constant. And then the second one starts the first time. And then what's the idea of a geometric sequence or series? What happens from term to term? Just so we remember what the nature of a geometric series is. We keep doing what each time? Multiplying by another r. To get the next term, you just multiply by another r. So geometric series are based on repeated multiplication. To get the next term, whether it's in the series or the sequence, you multiply by another r. So times r, times r, times r, times r. Okay? So this is our general form of a geometric series. We allow for a constant to start. And then all the terms are that constant times some multiple of r. Okay, so the question is, for what value of r does a geometric series converge? So first let's remember, for what values of r does this geometric sequence converge? Negative 1 to 1, right? So recall, for a geometric sequence, The sequence will converge to 0 if R is like a fraction, right? A percent, less than 100%, right? You keep taking a fraction of what you had before, that'll get small. So by the divergence theorem, we know for sure if R is outside of this range, and the sequence doesn't converge, then what about the series? Has to diverge, right? The only possible way that the series could converge is if what? The sequence goes to 0. So our candidates or our possible R values for which the series could converge is going to be these R values for which the sequence converges to 0. But is it guaranteed? It's not guaranteed. We have to do the math and figure out for which values of R does the series converge. Okay, so we're going to consider that's the kth partial sum. So I'm going to go a little fast, and you can go back to the video and pause it and take notes. So just want you to watch and absorb as much as you can. So this is the kth partial sum. We sum up to the kth term, which is AR to the k minus 1. And now I'm going to multiply both sides of that by R. So I'm going to multiply both sides by R. Why do I do that? Because it works, okay? It works to answer our question, and you'll see in a second. So I'm going to multiply both sides by R, and then I'm going to line up the common terms, and then I'm going to subtract. And so what I'm going to get is the kth partial sum minus R times the kth partial sum. All I'm going to get is 1A over here minus AR to the k over here. So we're just doing some algebra here, I'm going to factor out the kth partial sum. So it's times 1 over R. And then I'm going to divide by 1 minus R. So now I've got an expression for the kth partial sum. The kth partial sum is A minus AR to the k over 1 minus R. So this is a different way to get the kth partial sum rather than adding all those up. This is like right? It's a general term, right? This is the general term for the kth partial sum. Okay, so I'm going to split that fraction up into a difference using the difference of the numerators. So that's another way to write the kth partial sum. And remember what we said earlier in class. The sum of this series, what is the same as the limit of the sequence of partial sums, right? That limit of the sequence of partial sums, each term in that gets closer and closer to the sum of the whole series. So you keep adding on one more term, right? So we're going to look at the limit of, so here we're saying the series, the sum of the series is the same as the limit of partial sums, which is the limit of this expression we found, which is equal to the kth partial sum. Okay, and so then we ask, when does this, so really this is just a constant, these are just constant numbers, a over 1 minus r, those don't change. So the limit really applies to this second term as k goes to infinity. So when will this converge? So notice it's r to the k. What sequence is that? R to the k. Geometric. When does the geometric sequence converge? When? R is between -1 and 1. And what does it converge to? 0. So when this thing converges, which is r between -1 and 1, what happens to that whole term right there? Goes to 0, right? So the limit of that is 0 when r is between -1 and 1. And then that limit then equals this first term. So what did we find out? The sum of the series, if r is between -1 and 1, the sum of the series is a over 1 minus r. So that's when, so not only do we know when the geometric series converges, we know what it converges to. So when r is between -1 and 1, the same condition for the sequence, the series will converge. And now we also know what it converges to, a over 1 minus r. Okay, recall the turtle. What do? He walks half the yard the first day, a quarter of the yard on the second day, an eighth of the yard on the third day. So we want to express that when we came up, that was the series 1 over 2 to the j, right? So that is 1/2 to the j. What kind of series is that? This is a geometric. That turtle walking across the yard is essentially a geometric series. Okay, so but I need it to be in this form, a times r to the j minus 1. So I need to make that 1/2 to the j minus 1, but I still need this thing to be equal to this. So what else do I need if I just took 1 less 1/2 multiplied together? I need another 1/2, right? See that? I need another 1/2. So now I've got a r to the j minus 1. Does this converge or not? Yes, r is less than 1, greater than -1. My r value is 1/2. So what does it converge to? Oh, the sequence converges to 0, right? But what about the series? A over 1 minus r we just found, which is 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is? Does the turtle make it? Does he make it all the way across the backyard? Yes, he does. If he walks forever. But he's got to walk forever. If he walks forever, if you add up all infinitely many terms of this sum, you get 1. He makes it. As soon as he stops, he doesn't make it.